Over the past few decades, the domain of underwater robotics has experienced considerable expansion. Presently, the use of remotely operated vehicles has become safe and routine. These devices can carry various sensors and tools to perform underwater videography, corrosion detection without the need for direct human involvement, significantly reducing risk and cost. Another application involves playing a critical role in ensuring the safety and efficiency of oil and gas extraction processes. They provide eyes and hands in depths that are inaccessible to human divers, enabling complex tasks such as underwater welding, repairs, and the installation of equipment on the ocean floor. In addition to the marine environment, there are numerous categories of highly physically constrained underwater environments that must be accessed on a regular basis for purposes such as inspection, maintenance, repair, or decommissioning. A highly physically constrained environment is defined by limited spatial conditions, which may involve being enclosed by walls, narrow corridors, or areas filled with obstacles. In fact, many manual underwater operations can be replaced by underwater robots. In such cases, an accurate positioning system is essential, as effective autonomous navigation depends on regular, accurate position updates. An accurate positioning system allows any data from the sensor payload to be geospatially located, meaning that sensor readings can be repeatably mapped in the underwater environment and presented in human-readable formats, such as a heat map format. Even lower levels of autonomy, such as position and velocity control, which can provide smooth and accurate navigation in the presence of disturbances, also require precise positioning information. Classical approaches to underwater vehicle positioning include long baseline, short baseline, and ultra-short baseline systems. The long baseline system uses a network of fixed transponders on the seabed at known positions to facilitate precise location determination through acoustic triangulation. It operates by emitting acoustic signals between a mobile interrogator on an underwater vehicle and multiple seabed transponders, measuring the time it takes for these signals to travel back and forth. The short baseline system is similar to long baseline but with a different configuration and scale of operation. Instead of being spread out over large distances, the transponders are positioned relatively close to each other, often mounted on a single structure such as a buoy or a boat. In many cases, the buoy or boat is often equipped with GPS. It helps in accurately determining the positions of the transponders relative to the Earth's coordinate system. Unlike long baseline and short baseline systems that use multiple transponders, the ultra-short baseline system operates using a single transceiver mounted on a surface vessel that sends and receives signals to and from a beacon attached to the underwater object. However, in a confined underwater environment, these traditional methods used in marine settings may no longer be applicable. It will face many new challenges, such as the multipath effect. This occurs when acoustic signals emitted by a transmitter reflect off various surfaces, including obstacles, walls, and other structures in confined environments. When these multiple signals arrive at the receiver at slightly different times, they can cause errors in determining the precise location. Another issue is that, in indoor confined underwater environments, GPS is denied. Even when using systems similar to the short baseline, it is still not possible to accurately position the surface vessel. In response, both the academic and commercial sectors have conducted research on underwater positioning methods. A notable example is from the Hamburg University of Technology, which has developed a vision-based positioning technique. This method involves pre-deploying an array of fiducial markers in an underwater tank. A camera, mounted on the underwater robot and paired with the robot's inertial measurement unit, enables accurate positioning of the robot. Another approach is from Qualisys, which offers a high-precision underwater motion capture system. This system utilizes optical motion capture cameras positioned underwater, along with spherical markers mounted on the target underwater robot. The positioning accuracy of this system can reach sub-millimeter levels. However, these positioning methods either necessitate pre-installing infrastructure in the underwater environment or involve costly and complex precise calibration steps. Furthermore, the effective volume for positioning is fixed and limited. To enhance the automation of underwater robots, precise positioning is essential. CAP system is a confined space underwater positioning system that uses collaborative aquatic robots. A surface robot equipped with a LiDAR is used for self-localization. Additionally, to address any tilting that occurs during the movement of the surface robot, an IMU is also installed to estimate its orientation. Additionally, the surface robot is equipped with a downward-facing camera. It is used to perceive the underwater robot. The CAP system operates based on two principles. The first method involves using the downward-facing camera mounted on the surface robot to identify fiducial markers placed on the underwater robot. The pose of the underwater robot is then determined using existing pose estimation algorithms for April tag detection, such as the efficient perspective endpoint algorithm. Through our experiments, we have found that existing algorithms tend to have deficiencies in accurately estimating depth when applied in practical situations. Therefore, we proposed an alternative method. This method integrates the depth sensor on the underwater robot, which defines a plane. The coordinates of the fiducial marker, as projected onto the camera's image plane, allow the positioning of the camera in the world coordinate system to define a line. This line intersects with the plane defined by the depth sensor, pinpointing the exact location of the underwater robot. The validation tests were conducted at the RACO lab located in West Cumbria. The experimental tank is equipped with 6 Qualisys underwater cameras. This Qualisys system is used as the ground truth. Mallard is a 3-degree of freedom surface robot that is equipped with LiDAR, an IMU, and a camera. The robot being positioned is a customized BlueRov 2. It is fitted with an acrylic April tag on its top and also features a depth sensor on its enclosure. The surface robot is equipped with a LiDAR-based SLAM algorithm, enabling it to perform real-time self-localization. In the CAP system, the surface robot is designed to automatically follow the underwater robot, allowing for coverage of a larger positioning area. The automatic following algorithm, known as the virtual elastic tether, was developed by another part of our team. During the experiments, the underwater robot executed various trajectories, such as a square pattern and a lawnmower pattern. While moving along these paths, the underwater robot also continuously varied its depth, with changes within a range of 1 meter. Compared to the representative underwater positioning systems mentioned previously, the positioning accuracy of the CAP system is comparable. The CAP system does not require infrastructure or extensive calibration and is capable of covering a wider range. For additional results, please refer to the supplementary material.